What specific problem does the transfusion method aim to solve in the multimodal generative modeling domain, and what gap in existing research does it address?
The transfusion method aims to solve the problem of effectively integrating discrete and continuous modalities in multimodal generative models without information loss. Existing approaches, such as chameleon, typically quantize continuous data like images into discrete tokens, which introduces an information bottleneck and degrades performance. Transfusion addresses this gap by training a single model that simultaneously predicts discrete text tokens and diffuses continuous images, utilizing separate loss functions for each modality while maintaining a unified architecture. This end-to-end training allows transfusion to outperform traditional methods in both text-to-image and image-to-text generation tasks, demonstrating superior efficiency and scalability. Ultimately, transfusion provides a novel solution that enhances the generation of high-quality multimodal data, filling a critical void in the current research landscape.
How does the transfusion method work? Please illustrate the algorithm step by step, explaining the interaction between language modeling and diffusion processes throughout training and inference.
The transfusion method operates by training a unified model that integrates both language modeling and diffusion processes to handle discrete text and continuous images. During training, the model is exposed to both modalities simultaneously, applying next token prediction for text and a diffusion objective for images, with losses computed separately for each modality and combined using a balancing coefficient. The model processes text tokens through standard embedding layers and applies causal attention, while image patches are represented as sequences of vectors and utilize bidirectional attention. For inference, the algorithm alternates between two modes. In language modeling mode, it generates text token by token, and upon encountering a special beginning of image, boy token, it switches to diffusion mode, where it starts with pure Gaussian noise and iteratively denoises the image over several steps. This dual approach allows transfusion to generate coherent outputs across both text and image modalities without losing information, demonstrating its effectiveness in multimodal generation.
Can you walk through a simple yet illustrative example to demonstrate the inner workings of the transfusion algorithm, detailing both text and image inputs?
The transfusion algorithm operates by integrating both text and image modalities within a single model, utilizing distinct training objectives for each. For instance, consider a scenario where the input consists of a text prompt, such as "a cat sitting on a mat," accompanied by an image of a cat on a mat. The text is tokenized into discrete tokens, while the image is encoded into a sequence of continuous patch vectors using a variational autoencoder, VAE. During training, the model applies the language modeling objective to predict the next token in the text sequence and the diffusion objective to denoise the image patches, effectively learning to generate coherent outputs for both modalities simultaneously. When generating outputs, the model first samples a token indicating the start of an image, boy, switches to diffusion mode, and iteratively refines the image from pure noise to a coherent representation, before appending an end-of-image token, EOI, to signal completion. This process exemplifies how transfusion seamlessly combines text and image generation in a unified framework.
What are the key theoretical and practical benefits of using transfusion compared to existing methods such as the chameleon approach, particularly in terms of efficiency, accuracy, and scalability?
Transfusion offers significant theoretical and practical advantages over the chameleon approach by maintaining continuous image representations instead of quantizing them into discrete tokens, which eliminates the information bottleneck associated with discretization. This results in improved efficiency, as transfusion achieves better performance metrics, such as lower FID scores, with substantially less computational cost, up to 34 times less compute for image generation tasks. In terms of accuracy, transfusion demonstrates superior scaling laws across various benchmarks, outperforming chameleon in both text-to-image and image-to-text generation, while also achieving comparable performance in text-only tasks. The model's architecture, which integrates intra-image bidirectional attention, further enhances its ability to process and generate high-quality outputs. Overall, Transfusion's unified architecture allows for seamless multimodal learning, making it a more scalable and effective solution for generating and understanding both discrete and continuous data.
How was the effectiveness of the transfusion method validated or tested, including details on datasets, experimental design, metrics used for performance evaluation, and any baseline comparisons?
The effectiveness of the transfusion method was validated through a series of controlled experiments comparing it to the baseline model Chameleon, using a variety of datasets and benchmarks. The experiments involved training on a mixture of 1T text tokens and 3.5B image caption pairs, with performance evaluated on standard benchmarks such as MS-COCO for text-to-image generation, where metrics like Frechet inception distance, FID, and clip scores were used to assess image quality and alignment with prompts. Additionally, the model's text generation capabilities were evaluated using perplexity on held-out tokens from Wikipedia and the C4 corpus, as well as accuracy on the Llama 2 pre-training evaluation suite. The results showed that Transfusion consistently outperformed Chameleon across all benchmarks, achieving significant improvements in compute efficiency, with FID scores indicating better performance at lower computational costs. Furthermore, the model was also tested on the GenEval benchmark, demonstrating its ability to generate high-quality images while maintaining competitive text generation performance, thus validating its multimodal capabilities.
What specific results were achieved with the transfusion method in various tasks, and how do these results compare with state-of-the-art models such as DAL-E2 or SDXL?
The transfusion method demonstrated superior performance in various tasks, particularly in text-to-image generation, where it outperformed the Chameleon approach while using less than a third of the compute, achieving approximately 2 times lower FID scores. In image-to-text generation, Transfusion matched Chameleon at only 21.8% of the flops, indicating significant efficiency. Additionally, on the GenEval benchmark, the transfusion model surpassed other popular models like DAL-E2 and SDXL in image generation quality, while also generating text at a performance level comparable to Llama 1 on text benchmarks. The model's ability to generate high-quality images and text simultaneously positions it as a promising approach for multimodal tasks, showcasing its effectiveness over traditional models that separate modalities. Overall, Transfusion's results highlight its efficiency and capability in generating both discrete and continuous data without the information loss seen in other methods.